small number of large modules, which is probably very non-optimal. It might have something to do. Why it happens this way, we don't know. Can any of you suggest a possible reason why this distribution is encountered in actual practice? Why do people tend to have a large number of small modules and a small number of large modules? I don't have a good explanation for why. Only thing is that that's what we have observed a number of times. So that is one thing that could be very interesting to think about. And I guess nobody has thought about it so far.
Dr. Malaiya, how many data sets have you observed?
Oh, this behavior?
Yes, sir.
So we looked at two of them here. Garusi library and there was given data by Vasily.
Is that statistically significant, only 2 data sets?
There are 2, and then we have seen other data where it again follows the same pattern.
Okay.
So my suspicion is that, if you look at Garusi library, it is not contribution of a single individual, but it's a contribution of a number of individuals working on different things. They came up with something and gave it to the Garusi library.
Okay.
So it is something that came from diverse sources, and somehow it has this pattern. And pattern is so nice. So that means there is something going on, which I'm not sure what it is.
I think because when we do a program and then like in software, there is some common small functions that we call frequently. Then I think like these are the ones that represent the small modules that exist, and there is the more complex like main code that calls these functions, which will be like 1 or 2 of them that calls these. So there will be few larger modules and many smaller ones.
Oh, okay.
Yeah,
so I think it has something to do with how people think,
yeah,
or how problems naturally arise. Probably somehow the way problems divide a number of computational pieces of problems,
but decomposing
they translate into small modules.
Yeah.
Or so there's some reason which I'm not exactly sure.
You know, because intuitively, like when we have a problem and we do like a program or a software for that, we tend to do a functional decomposition of the problem.
Right,
and this is what exactly will give us smaller, like many small modules and then few larger modules. That could be the functional decomposition.
Oh, okay. So incidentally, if you have some data, so try, so do you have one of those programs that will count the number of lines? So see how the distribution looks like in the project that you have encountered. I know that there are some examples that I have seen where this is not true.
Oh.
So for example, there is a paper written by some people, and they mention a particular project, and in that project all the modules are approximately same size. So they probably had some programming discipline or some order by the manager that make all the modules of the same size. And but that is, I think I have seen only one example. So they probably had some discipline to enforce that. But this is something that naturally arises. And okay, but that is, so yeah, actually, this is, as I was saying, the people haven't studied this, and would be rather interesting to see. Now this problem actually has nothing to do directly with the dependence of module size and defect density, because it's just distribution of module size. Right. But why it has this nice pattern, that makes us wonder. And I think this is something that perhaps we should look at sometime. But okay. So now, how does this impact the overall defect density in a project? So now let us suppose that you have a project where modules sizes are distributed like this, and this is type of dependence you have on module size versus defect density. Then the overall defect density would look like this. Now I'll give you the mathematics here. And for you don't need to worry too much about so overall defect density. Don't worry too much about how I got this equation, although, okay, so I will represent this as, this is the density function. Assuming smallest module size is size 1, and we integrate. So basically, G is some parameter that you can get by fitting this. Incidentally, the value of G we found in some of our numbers somewhere around like 0.00, I'm just picking up some number, something like this. M is the total number of modules. (10⁻³ accounts for the fact that the defect density is measured in terms of per 1,000 lines of code and divided by the total size. So this gives the total number of defects, and this is the total size. And so you can use this expression, and so now if, let us say that you can, let's assume that you want to control the, you want to optimize defect density by controlling the module size. The ideal thing would be to have each module, the size of each module equal to whatever is the optimal module size. So that would be the optimum. But of course, as we have seen, this is the typical. So if you wanted to do something about this problem, what you could do is do this. Merge the small modules into larger ones. And so that will get rid of some of the defect-prone modules. And we had mentioned about a model for static model for defect density. So if you want, you can have a submodel. So this is the submodel. For defect density. Sorry about that. That would be equal to where A, B, and C are appropriate parameters.
So for the graph over there, do we have diagram? So the distribution of the module count versus the module size is the same as the density, the defect density. They have the same.
Can you say that again?
So like initially, that represents the module count versus the module size, the distribution. Right?
The defect count versus module size, the one I had earlier.
I mean, no, this one.
Oh, this one here?
Yeah. So this represents the module count versus the module size.
Right here.
And it's the same one represent, is it the same like for the density, the overall?
No, there are two different, there are two independent plots.
Okay.
So there are two independent plots, so that's why I read this multiplication.
Oh.
So I have this represents the earlier plot. So this is the defect density versus module size plot. And this term here, this and this here, this represents the effect of module size distribution. So there are two effects that this integral includes. Okay, so let's go to the next topic then. And let's see what should be the next topic. Oh, there was an analysis done by Rosenberg, and maybe I can just skip it. So there was a paper, and in this paper, he concluded that he did not see a relationship between module size and defect density. And so what he did, now actually his analysis is wrong, and I guess I should not be teaching you wrong stuff, but since I am looking at it, I might as well mention it. So, so he did an analysis, so he assumed that x and y are statistically independent, and he made a scatter plot of y divided by x against x, and basically, so he assumed that x, y is the number of defects, and x is the module size, and they are independently distributed. And he made a plot of y divided by x against x, and he showed, well, see, there's no, it looks like, he said that it doesn't seem to fit any relationship, but what he was actually assuming that he was actually assuming that a module size, defects in a module is independent of the module size in his analysis. So basically he was in effect assuming that defect density is inversely proportional to module size. So in fact notice that when I talked about when I gave you that expression for the module-related defects. So he basically assumed that all the defects, what he was assuming amounts to what I have mentioned about module-related defects. But that is only a part of the picture. Okay.
So, is there any study that takes into consideration the type of the defect? Because like in software, when we have a set of defects in a software, then like some studies suggest that maybe like more than, for like the majority of the defects are not severe, and only few of these are the severe defects, and we need to focus on these. So did the studies focus on the type, the severity of the defect?
Yeah, so we didn't look at the severity of the defects. So that is actually another dimension.
Yeah.
So sometimes you look at severity of defects. And incidentally, in software reliability engineering, sometimes people look at severity of defects. So they have used two different approaches. So in one approach, they will simply consider defects with high severity and not consider others, if they're interested only in high severity defects. This type of question also arises in security vulnerabilities.
Right.
And other approach people take is that they would, for each defect, they will multiply it by a number that will represent its severity.
Yeah, it's a weight.
And in fact, some people will apply software reliability growth model to this, not for the number of defects, but weighted number of defects.
Mm-hmm.
Defects weighted by the severity. So that is something that some people have done.
Mm-hmm.
So yeah, but that is another dimension which sometimes it would be useful if you are interested in making a distinction between high severity and low severity defects. Okay, so let's next go to the next topic, and the next topic is the next topic is the connection between test coverage and software reliability.